Hello, Professor. My name is Matthew Bowers. I'm going to be talking about my algorithm analysis project for the semester. Um, since you kind of came in mid-semester, I'm going to start from the beginning, kind of what I'm doing, and then I'll walk you through some of the code. So I decided to do a project that was suggested by the previous instructor, and it was called a flight network as a directed graph. Um, Here's a table of contents. And so basically, I'll get into the problem statement in just a little bit. But my motivation for the project was I was really, really interested in graphs. I really liked graph theory. When I took discrete math, I really liked the graph theory section. And so when this project idea was proposed, I instantly jumped on it. I thought it would be pretty beneficial to me because even though I really like graphs, I'm not so confident coding graphs. I don't have so much experience with that. And then another motivation for this was like interview questions. I know that for software engineering interviews, graph questions come up pretty often. So knowing how to implement them, knowing how they work at a deep level is pretty important. And so this is going to be kind of the objective of the project and the outline, the problem statement. So the problem statement was to create a weighted and directed graph that contains flights as like the edges, and then the nodes or vertices are going to be like airports. So you have one vertex, and that connects to another vertex, and then in between you have an edge, and that edge weight is going to be how long it takes to get to that other airport. So let's say from Atlanta to Chicago, the airports, it'll take 2 hours, something like that. And so overall, I had to create a graph that contained 10 airports or 10 vertices, and all of the lines going out of the airports, going into the airports, they all had to be directed, they all had to be weighted. Um, and then, so yeah, I had to do that for 10 airports and then for 20 airports, or just like the vertices. Um, and, my thinking with this was if you get 10, you should be able to get 20 just because um, you write the function so that it takes in any parameter, no matter how large, and it'll compute it, well, given constraints. Um, and so just walking a little bit more into the problem formulation, I had mentioned three algorithms. I mentioned Dijkstra's algorithm. That was like my go-to algorithm. I mentioned depth first search and Bellman-Ford. Um, in the end, I decided to use Dijkstra's algorithm and Bellman-Ford, just because with depth first search, it really wasn't giving me what I wanted in the end. So in the end, I wanted to calculate the cost of each like vertex going out to other vertexes or vertices. So with Dijkstra, you get the cost. So you enter in two airports, and you get the cost, the optimal cost, the minimal cost of going from one airport to the other. And so you get the number of hops that you do, or the number of hops that you make. You get the path of airports that you traverse to get to the end from start to finish. And then you also get the final cost. And I decided to choose Bellman-Ford because even though it's really similar to Dijkstra's algorithm, it differs a little bit. Um, with Bellman-Ford, basically you give it a node or an airport or a vertex, and it will find out the shortest path to get to all of the other nodes, and it will turn back an array or an object of all of the shortest distances or weights or whatever. And I'll demonstrate that in a minute or two. Um, to implement this project, I used something different. I think a lot of other people used Java or C++, maybe even Python. I decided to use JavaScript. I really like JavaScript. It's probably my favorite language. I have a lot of experience using JavaScript. I had an internship where I used JavaScript. Um, it's just my favorite language. I really enjoy using it. And whenever I code in JavaScript, it just flows. I don't know. I really like it. Um, so yeah, I talk about how if I decide that JavaScript is not the correct choice, because I know that with algorithms and data structures, many people use C++, Java, and not JavaScript. So if I decided that JavaScript was not the correct language to use, I would switch to something else. Um, and so this was in the document before when we had our previous professor. So I decided to keep this in just to kind of like go through my thought process. Um, and then talking a bit about libraries, um, I did not think that libraries would be required in the beginning, but I in the end I did use libraries. I used one where it was really easy to just make a graph. So in the beginning, I created my own class with that created a graph. I had functions that added vertices, edges, all that stuff. Um, but it was really time consuming, and I found a package called where is it? It is called. It might be further down, but the package is called Directed Graph, and that's exactly what I needed. And so I decided to use that package just to create the graph because it saved a lot of time. Um, and yeah, this is just kind of like the computer I'm using. I'm using a MacBook Air. This was just specified in the requirements, and I'm using VS Code. So this is all the implementation stuff. I'm not going to go through all of this just because I'm going to demonstrate it. I'm going to show you, but I'll briefly scroll through it. And so, like I said, I'm gonna jump into VS Code. I'll get to this at the end, but I'm gonna jump into VS Code right now. And so, right now, this is my index.js file. So this is like the main file of the project. I have a bunch of other files here, as you can see. I have kind of instructions on how to run this, but I'm gonna do it live for you. I guess kind of live. Um, but first, I kind of want to talk about these files. So this is the main file, but I have a bunch of other files that they're like helper files, controllers. Um, this is where the algorithms actually live. So I'll go over those first. Oops. So this is Dijkstra's algorithm. I decided to make it take a graph and then the departure airport and the arrival airport. So like the two nodes or the two vertices. And so I tried to do this execution time thing. It ended up being very negligible because the times were so fast. It's like 1 to 2 milliseconds execution time for this function. So, but it's there. Um, so yeah, I just have kind of all of the basics set up for Dijkstra's. I've got an array for visited vertices. I have all of the weights or like the distances between airports or nodes. I have all of the previous airports, so I can go back and like trace, like get the path. Um, and yeah, I just walk through Dijkstra's in here. Here we have the while loop, which is just kind of like while there is a nearest airport, keep it going, and if there is no nearest airport, then it'll stop, and that's the end of it. Um, and yeah, I have some helper functions here too. So here I get the shortest path, and this is just kind of to reiterate through it, and then I reverse it um, to get like the path, but backwards. So that's like the actual traversal. Because as soon as Dijkstra starts here, it's going to start at the origin. So it's going to start at the starting airport. And so it's going to keep adding and adding and adding, and then I want to reverse it so that I can get the proper order where it was traversed. And yeah, so I have a function for finding the nearest neighbor there. And then these exports, this is so that I can use this file, this function, in index.js. So I export it right there. And the exports are pretty easy to use. And so now going on to Bellman Ford. Excuse me. Bellman Ford, it takes in an array, and a string. I kind of have the parameters up here. So an array of vertices, an array of edges, and a string, which is the starting airport. Again, I just kind of have the basic setup. You have something for the weights. I still have some console logs here from when I was testing. And then you're going through here and you're setting all the values to infinity, similar to Dijkstra, because they haven't been discovered yet. We don't know what they are, but the main part is with relaxing it. And what relaxing it does is it increases the accuracy of like the distance to the next airport. So it continuously shortens the distance that is calculated between the vertices by comparing those distances with other distances, if that makes sense. So I have notes on the other screen just to keep myself focused and on track. But yeah, so this is the part where I relax all of the. I should put a comment here where I'm relaxing the equation, and then this is also just in the pseudocode. In my case, I don't really need it just because negative cycles will not exist. Mostly because I'm the one creating the airports. I'll show you that in a second. But yeah, I wasn't really sure if I should include it, if I shouldn't, but I figured it would be best practice to include it. So yeah, I included it, and if there happens to be a negative cycle, I'm just going to return undefined because I want the program to just not even count that because it's a negative cycle. You can't have a negative distance to an airport. So yeah, and again, I have these time things to try and get the execution time, but it is so small that it is negligible. And at the end, I'm returning the distance in the form of an object called weights and the execution time. And then also in Dijkstra, I am returning the shortest path result, which is also an object, and you have the weights, so like the final calculated weight. You have the path, and then you have the execution time. So I wanted to quickly show the airports. I put these in separate files just because they're so long. So this is where I pull in that package that I was talking about, or the library. It's called Directed Graph. And this just makes creating a graph really easy. So you just instantiate it, you say new graph, and then it has a bunch of built-in functions for a graph. You have add vertex, you can add edges. One interesting thing that I had to do was I had to customize one of the functions. So I customized that down here. Just because when I'm doing Bellman Ford, when I'm doing this one, I need an array of vertices and an array of edges. And so what I decided to do with customizing this is I made an edge array because before it was really difficult to access those edges because it's all in object notation. It was just a real pain to access those edges. So I decided to customize this function. So the original function is just set weight, and you give it you give it node A, you give it node B, and then you give it a weight between the nodes. And then I went one step further just to make my life easier in Bellman Ford, and I pushed the created object to edge array. That way it would be easier for me to access an array when I do Bellman Ford. I hope it's clear why I did that. If there are any questions, you can feel free to email me. And then again, I'm exporting the airports and the array. And so yeah, it's a lot. It seems just like a ton of code, but basically what this all is doing is it is making this graph. So this is what the actual object looks like. So if I were to print this out, it would just look like this. That's what it would look like. In fact, let me see. Live demos never go well, but we can try it out. Airports 10. There we go. So we have the same graph. I just copied it and pasted it up here just so that you can, so you know what it looks like. I want to comment that back. Um, and so yeah, that's what the graph looks like. And basically, how we can interpret this is the starting node is, or the starting airport is Atlanta, and Atlanta can go to Boston, and Atlanta can go to Chicago, and they both cost 2. And something that I actually did was I looked up the flight distance for every flight, and I have 20 flights. I looked up the flight distance for every flight. And so all of these hours, all of these weights, all of these distances are actual flight times. So it does take about 2 hours to get to Boston, 2 hours to get to Chicago from Atlanta. Um, I've been to London a couple times from Boston. I've had layovers in Boston, and it takes about 7 hours to get to London, depending where you have stops. I've also been to Moscow from London, and it takes 4 hours. So I looked up all of these flights, and I put that in there just so I don't know. You can get the actual flight time if it's something you're interested in. And Airports 20 is the same exact thing, but this is the 20 airports version. So I have all of the same airports, all of the same edge weights, plus some more. So I have some extra airports added. I have LED, which is St. Petersburg, Shanghai, Toronto, Ottawa, Lyon, which is a city in France, Stockholm, Helsinki, etc., etc. So I just added some more airports. I added some more connections, and that's what we get. So now, previously Atlanta was only going to Boston and Chicago, but now Atlanta goes to London, Atlanta goes to Toronto. So so yeah, that's kind of those two graphs working. And now we get into the main file here. This is a built-in package for uh, Node.js, which is like a framework for JavaScript on the back end. Um, and basically, what this does, it allows you to read terminal input. So here, I'm just importing that in, and then I'm getting all of my required functions and files in from all of these other folders. So we got the actual functions Dijkstra and Bellman Ford. We have those the airports that I was talking about just previously. We have the edge arrays, which is important for Bellman Ford, and all that good stuff. I decided to make my program command line. I didn't really want to hard code anything, so this part is a mess. I know, but basically it's just asking for user input. It's doing very basic validation checks. So basically, right here, I'm getting an array of all of the airports in the 10 airport graph, and I'm confirming that whatever the user types in here, it's in that graph. And so, if it's not, then I close the terminal and I say that you should have to restart it. But let's assume that the user types something in, it's in the array. Another good practice is to make sure that all the user input is obviously, if the user input is good, it's in the correct form. Because all of my airports, as you can see, they're all uppercase, they're all capitalized. So if a user were to type in lowercase letters, it wouldn't work. So that's why I added this, so that everything that the user types in is going to be, I guess, casted into uppercase, so that there are no issues there. Um, and so yeah, I kind of just go through. I'm saying, select your departing airport, select your arriving airport, and then in here I run Dijkstra and I run Bellman Ford. And then I do the same thing for the 20 airport graph, asking the same questions and so on and so forth. Yeah, this part is a bit of a mess, but um, it's the command line input stuff. So I also wanted to add that basic validation to make sure that nothing really broke. I also have some, lastly, before we actually get to the testing, I have some helper functions just to clean up the code a bit, so I can just say, Dijkstra helper instead of writing all of this code. And basically, what all this code does is you give your departure airport, your arrival airport, and your graph, and then you just get the result. Um, so you get the total distance, you get the path, and you get the execution time. That should be a 1. Just catching the mistakes. Um, so for hops, it's like however many times it takes you to get to the airport. So let's say you want to go Atlanta to London. So you go Atlanta to Boston to London. That's 2 hops because you go to Atlanta. You go from Atlanta to Boston. That's 1 hop, and then from Boston to London, which is 2 hops. And so that's what the hops is. It's just calculating, how many stops there are until you get to the final airport, basically. Um, and then the path that is returned from this object, it just doesn't really look good. So this is just kind of to format the path better. It uses an arrow to make it look like it's going in a directional way. Um, so yeah, that's the Dijkstra helper, and then I also have one for Bellman Ford, very similar. Um, Again, with Bellman Ford, I'm asking for an input graph, and then I get all of the keys or the vertices in this case from that, and then I give this vertices array to Bellman Ford. And JSON stringify, it just kind of it's nicer for formatting. So without further ado, let's test it. So I'll run it a couple times just to, be sure. To run it, we're going to do node index.js. And then you'll see that it says functions for 10 airport graphs. So this is the one that's only going to be 10 vertices long, or 10 airports long. So first I'll start with like bad input. So if there's bad input, then the program just closes and it says the airport you selected was not in the list I provided. So I'm going to run it again, and I'm going to select Atlanta. You can see here that I typed in lowercase, and so that validation is good. And let's say we want to go to Madrid. I'm just going to type uppercase for, everything is good. And so it spits out this, and so you can see here that we typed in Atlanta. We want to go to Madrid. That's our arriving airport. And here we have our Dijkstra's algorithm. And it says that the optimal distance between ATL and Madrid is about 14 hours of travel. And this is going through Boston to London to Berlin and then to Madrid. Obviously, in the real world, you would just probably go to Atlanta to Boston to London and then to Madrid, but I didn't have a path for it. So all the paths are just kind of random. But the flight time is actually real. So if you were to fly this, it would take about 14 hours of travel. And then the fewest amount of hops is 4 because you have 1 hop, 2 hops, 3 hops, and 4. And like I said, the execution time is basically negligible. Sometimes it's 1, most of the time it's 0. So yeah. And then next we have Bellman Ford. And so Bellman Ford is just, it's telling you the distance to the other airports from ATL. Since your departing airport was ATL, Bellman Ford will take this value and automatically give the paths to the other airports from that initial value, which is ATL. So you can see that the optimal value for from ATL to ATL is 0 because it's itself. Going to Boston to Chicago, it's 2. Going to Moscow, going to Paris, it's 13. London is 9, etc., etc. And I wrote in the document that you can kind of validate it. So obviously with Dijkstra's, the optimal distance between Atlanta and Madrid is 14 hours of travel. And Bellman Ford calculated the same thing. So you can see this as Atlanta to Boston, Atlanta to Chicago, Atlanta to Moscow, Atlanta to Paris, Atlanta to Madrid, which they're both 14. So we're going to do this for the 20 airport graph. We want to go from Dublin to Ottawa. And we can see that the optimal distance between Dublin and Ottawa is about 11 hours. We can follow Dublin to Paris, and then go to Paris to Toronto, and then from Toronto to Ottawa, and we can do that in 3 hops. We also have the shortest path to all other airports from Dublin. And again, we can verify that this is 11 hours of travel from Dublin to Ottawa. If we look at Ottawa here, and we can see that the path from Dublin to Ottawa is 11. All the way to Shanghai, it's 31. So that's a really long. I would imagine that. Let's see. There's so let's run it again, and let's just get to that point again. So we want to go from Dublin to Shanghai, because that was 30 something hours. Yeah, 31 hours. So we would have to go from Dublin to Paris to Toronto to LAX to Shanghai. This seems pretty inefficient from like a point of view of actually traveling there, but how I have it set up, how I decided to add the edge weights, that's the most optimal path from Dublin, Ireland to Shanghai. On that note, that is it. I guess kind of the final reflection, just kind of a summary of what I did. And I talk a bit about the time efficiency. So I talk about for Dijkstra that the time efficiency would be big O of the vertices squared, but that is only if you're using an adjacency matrix. I'm right here. But I'm using an adjacency list. So the time complexity for an adjacency list would be big O e to the log of n, or e log of v, where e is the number of edges and v is the number of vertices. And it is this because we have to execute, we have the 2 for loops, which would, theoretically make it n squared, but you have to take into account that we're executing a lot of the dependency for how many times it's executed depends on how many e's and how many v's, or how many edges and how many vertices there are in the code, or are in the function that's being executed. And then Bellman-Ford takes in an array of vertices and an array of edges, also like a starting place. And so this is also very heavily dependent on the edges and the vertices, and the time complexity for this would be big O e times v, where again, e is the number of edges and v is the number of vertices. To wrap up, I really enjoyed the project. I really enjoyed being able to feel comfortable with graphing algorithms and being comfortable with implementing them. That was one of my goals for this project, is I wanted to become more familiar with graphing algorithms while writing code. I understood them from a high level, but I wanted to get down to a low level, get down to writing code. And now I completely see how to implement these graph algorithms in code. And I understand the importance of these graph algorithms all the way from Google Maps telling you the fastest way to get to Chick-fil-A or something, all the way to the big systems like the World Wide Web and routing and all that stuff. Without graphing algorithms, things would look a lot different. And so on that note, this whole section for implementation is what I did down here, or what I did. Oh, that is the wrong VS Code. That is what I did here explaining. So that's that. And yeah, I'm not sure how long the video is supposed to be. I hope it is within the limit. I really like to go into detail when I explain things. So so yeah, that wraps up the project, and that's it. Thanks for listening.